morning everyone. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the today's lecture, we are going to learn about reflection and refraction of uniform plane waves, or reflection and refraction of the electromagnetic waves. In this, we are going to learn about how the normal incidence of a plane wave in the dielectric media we are going to learn in this particular lecture, right? So before going to analyze the normal incidence at a plane dielectric boundary, first of all, what do you mean by reflection and refraction of a uniform plane wave? Then we'll move on to the actual topic which we are going to learn in this particular lecture. So the topics which we are going to cover in this particular reflection and refraction of uniform plane waves is a definition of a reflection and refraction of uniform plane waves, then normal and oblique incidences. So in this normal incidence case, we are going to discuss about normal incidence at a plane dielectric boundary and a normal incidence at a plane conducting boundary. And similarly, in the oblique incidence case also, there are two important topics or cover in this particular oblique incidence, that is parallel polarization and perpendicular polarization. Those two are also called as horizontal polarization and vertical polarizations. Then after that, Brewster angle, then critical angle and the total internal reflection, then surface impedance, then after that Poynting vector and Poynting theorem, then some of the applications based upon this Poynting theorem. Then we are going to learn about power loss in a plane conductor, right? So reflection and refraction. So generally the waves are of three types in this case. In order to analyze the reflection and refraction of a uniform plane waves, one is incident wave, and reflected wave, and third one is transmitted wave, right? Depending upon these three waves, we are going to study about reflection and refraction of a uniform plane waves. So when the incident wave, normally waves or travel, or normally waves are nothing but it transports energy from one place to the another place, or it sends the information from source to the destination. So now to send that, we just consider the general wave means incident wave. When it touches the boundary or it strikes the boundary, part of that instant wave is reflected back to the same medium, and part of that instant wave is to be transmitted to the next medium. So in order to analyze this reflection and refraction of uniform plane waves, we are supposed to consider the homogeneous media or isotropic type medium, right? So now, when a light wave strikes a smooth interface of two transparent media, like means examples of that two transparent media are called air is nothing but free space, and glass, water, etc. These are all the different examples for the media, and the wave is in general the partly means that incident wave is partly reflected and partly it is to be refracted, nothing but transmitted. Means refracted wave is also called as transmitted wave, right? Next, if a transmission line having a characteristic impedance Z0, means in order to analyze this reflection and refraction, we need to consider two impedances, as one is Z0 and one more is ZL. Where Z0 is said to be characteristic impedance and ZL is load impedance. If these two are equal, what happens? If these two are not equal, what happens? Means if two are equal, which is to be obtained, which is to be occur, reflection or refraction, which is if these two are not equal, which is to be occur, means whether reflection or refraction. Depending upon that, we are going to analyze this one. Means if a transmission line having a characteristic impedance, means that characteristic impedance is denoted with Z0 and the line is terminated, means the load generally we used to consider at the output side, and it is represented with L, right? So impedance is generally represented with Z, and the load impedance is denoted with ZL. So if ZL is not equal to Z0, then there is no mismatch between the two impedances and the line is not properly terminated. And this is the case, we can say that means reflection occurs. Means if load impedance is not equal to the characteristic impedance of that medium, then reflection occurs. Means part of the wave is reflected back to the, bouncing back to the same medium. That phenomenon is said to be here reflection, right? Then next, if ZL is not equal to Z0, means load impedance is not equal to the characteristic impedance Z0, then the line is said to be properly terminated, and this is the case, part of the incident wave is transmitted to the next. Means this is the case, refraction occurs, right? So if ZL is not equal to Z0 case, reflection occurs, whereas if ZL is equal to Z0 case, load impedance is equal to the characteristic impedance case, then the line is said to be properly terminated, and the condition or the case is to be termed as refraction, right? So depending upon this reflection, refraction and transmission and incidence, see types of incidences, means how it is to be touches, how is to be strikes the boundary. Suppose if we have, this is the boundary, if we have the boundary line as like this, below this boundary we have medium 1, and above this boundary we have medium 2. So if the incident wave is touches the boundary, what happens? Means let it be, suppose if this is incident wave and it consisting of two waves as well as nothing but reflected wave as well as the transmitted wave. So part of this is to be transmitted, means part of that incident wave is reflected back to the same medium, means that wave is said to be your reflected wave. Means this is the case, ZL is not equal to Z0. And part of this is to be transmitted to the next medium, hence it is called transmitted wave or refracted wave, right? So when a uniform plane wave is incidences, means in this we are going to learn types of incidence. So there are two types of incidence cases occur. One is normal incidence and another one is oblique incidence. Now what do you mean by normal incidence and what do you mean by oblique incidence? Normal incidence means when a uniform plane wave is incidences normally to the boundary, strikes the boundary normally between the two media, then it is known as normal incidence. Coming to the oblique incidence, means there is some objection between medium 1 and medium 2. Because of this incidences occur, that is when a uniform plane wave is incidences obliquely to the boundary between the medium, then it is known as oblique incidence, right? So there are two types of incidences for there, normal incidence and oblique incidence, right? So now first case we are going to learn about normal incidence, means normal incidence at a plane dielectric boundary. So normal incidence is to be considered in two different cases. Normal incidence is to be considered in two different cases. One is related to dielectric boundary and second one is conducting boundary, right? So dielectric boundary case, we are going to assume the both medium 1 and medium 2 are to be homogeneous. Let it be dielectric medium only, means medium 1 and medium 2 are two dielectrics. Whereas in the case of normal incidence at a plane conducting boundary case, one of the medium is to be assumed as a dielectric medium and another one is to be considered as conducting medium. So if one medium is dielectric and the other medium will be conducting, how the waves are to be transmitted and how the waves are to be reflected back to the same medium. So before going to discuss about that conducting medium, firstly we are going to learn about normal incidence at a plane dielectric boundary, right? So basically types of incidences are of two types, normal incidence and oblique incidence. Under this normal incidence, we'll have the first case as normal incidence at a plane dielectric boundary. Means here medium 1 and medium 2 both are two dielectric medium. Dielectric medium 1 and this is dielectric medium 2. Right? So between two dielectric media, we are going to analyze this normal incidence, right? So basically, what are the characteristics of this two media? Or means, firstly, we are going to consider epsilon 1, mu 1 and sigma 1 for the dielectric medium 1 characteristics, and for medium 2, epsilon 2, mu 2, sigma 2. Depending upon these three characteristics, permittivity of the medium, permeability of the medium, and conductivity of the medium, depending upon that, we are going to analyze, right? So for a dielectric medium, what is the value of sigma? As we have know that this propagation characteristics and all already we have learnt. So that is according to that, for a dielectric medium, sigma is equal to 0. Means for an ideal value of conductivity of the dielectric medium is assumed to be 0. Hence, both the mediums are representing with sigma equal to 0 only, right? So for medium 1, epsilon 1, mu 1 and sigma 1 are the three characteristic parameters. Similarly, for medium 2, these three are given by epsilon 2, mu 2, sigma 2, right? So if you observe clearly in this particular y means z is an interface, z is equal to 0. This interface exists between two media, that is dielectric medium 1 and medium 2. So below z equal to 0 means z is less than 0, we have medium 1, and above z equal to 0 means z is equal to greater than 0, we have medium 2. So if you observe in this particular medium 1, we have two waves. One is incident wave, which is representing with HI and EI, and the unit direction is represented with ANI. And similarly, another wave is representing as here is reflected wave, and two field components are represented as ER and HR. And the normal unit vector is represented with ANR. Okay. And means if you observe in the medium 1, we have two traveling waves. One is incident wave and another will be reflected wave, right? So incident wave is touches the boundary as like this. This is incident wave, and reflected wave means that is this is reflected wave, right? So this reflected wave is to be considered as the field components. Means now to analyze this one, we have considered two field components as electric field intensity as E and magnetic field intensity as H. For the incident wave, these two components are represented with EI and HI, where I stands for incident wave. Similarly, ER and HR are the two field components of reflected wave, and it is represented with ER and HR. Means if you observe particularly at z is equal to 0, there exists an interface, and below z equal to 0 we have one medium, and above z equal to 0 medium 2. If you observe here in the z is less than 0 case, medium 1 means medium 1 consisting of two traveling waves. One is incident wave and another one is reflected wave. And if you observe in the medium 2, we have only transmitted wave, that is only one wave is exist, that is represented with ET, and transmitted wave of the magnetic field intensity as HT, right? So if you consider the normal incidence, see when the incident wave strikes the boundary, part of the incident wave is reflected back to the same medium, and part of that incident wave is transmitted to the next medium, right? So based upon this, we can write the equation as EI is equal to ER plus ET. Why? Because instant wave field strength is a combination of reflected wave field strength as well as the transmitted wave field strength, right? So in the medium 1, we have two traveling waves, and in the medium 2, we have only one wave, that is called transmitted wave or refracted wave. Okay. So based upon that diagram, we are going to consider some of the assumptions as A uniform plane wave striking the interface between the two dielectrics at right angles, and a uniform plane wave travels along the plus z direction and incidence at right angles at z is equal to 0. Means at z is equal to 0, that interface is separating between two medium. Right? So below z equal to 0, let the properties of the medium 1. Why? Because below z is equal to 0, we have medium 1, and the properties of the medium 1 are to be represented as epsilon 1, mu 1, sigma 1, and eta 1. As we know that epsilon 1, mu 1, sigma 1, and eta 1. So permittivity of the medium 1, permeability of the medium 2, medium 1, and conductivity of the medium 1, followed by intrinsic impedance of the medium 1. In the similarly, at above z equal to 0 means below z equal to 0 we have medium 1, means above z equal to 0 we have medium 2. So let the properties of this medium 2 be represented with epsilon 2, mu 2, sigma 2, and eta 2, where epsilon 2 permittivity of the medium 2, permeability of the medium 2, and conductivity of the medium 2, followed by intrinsic impedance of the medium 2. As we know that intrinsic impedance eta is equal to, it is the ratio of electric field strength E to the magnetic field strength H. Right? So depending upon these properties, we will write the equations, mathematical equations for two constants, as one is tau and one more is gamma, where tau is said to be transmission coefficient and gamma is said to be reflection coefficient. And tau is given by here, it is the ratio of Et by Ei, and gamma is nothing but it is the ratio of Er by Ei. Right? As we know that Et, Ei, Er are transmitted wave field strength, reflected wave field strength, and incident wave field strength respectively. Right? So depending upon this, firstly, let Ei and Hi be the field strengths of the incident wave striking the boundary. First consider, let Ei and Hi. What is E stands for and H stands for means here electric field strength and magnetic field strengths are respectively denoted with E and H. And I stands for here incident wave. Hence, let Ei and Hi be the field strengths of the incident wave striking the boundary. Right? Touches the boundary. And let Et and Ht be the field strengths of the transmitted wave in the medium 2. Right? So the transmitted wave is aligned in the medium 2. Hence, we have considered Et and H2 to be in medium 2. Similarly, Er and Hr be the field strengths of the reflected wave in the medium 1 returning back from the interface. Right? As we know that incident wave is combination of two waves called reflected wave and the transmitted wave. Right? So part of this incident wave is reflected back to the same medium. Part of this incident wave is transmitted to the next medium. Hence, in the medium 1, we have two traveling waves. One is incident wave and another one is reflected wave. And in the medium 2, we have only one wave, that is transmitted wave. It is also called as a refracted wave. Okay. Then, for medium 1 and medium 2. So, in order to write the mathematical equations for transmission coefficient and reflection coefficient, we need to use boundary conditions between two dielectric media. So, this already we have learned in the electrostatics case, that is the boundary conditions between two dielectric media. There we have got two boundary conditions, as one is Et means E1t equal to E2t, and another one is B1n is equal to B2n. Tangential components of field 1 and field 2 are continuous across the boundary, and normal components of magnetic field flux densities are continuous across the boundary. Depending upon these two, we will write this one d1t by epsilon 1 is equal to d2t by epsilon 2. Similarly, from this, mu 1 h1n is equal to mu 2 h2n. Right? So, tangential components of electric flux densities of both the medium are discontinuous, and normal components of the medium magnetic field intensities of both the medium are discontinuous across the boundary. So now we have considered here continuous case. Hence, the first two boundary conditions we are supposed to consider. One is E1t equal to E2t and B1n is equal to B2n. Right? So for the medium 1 means from the medium 1 we will write here E1 is equal to what is the magnetic field intensity which is exist in the medium 1 means it is a combination of EI plus ER. Why it is the combination of EI plus ER? Why? Because in the medium 1 we have two traveling waves. One is incident wave and another one is reflected wave. Right? So in the similarly magnetic field intensity which is exist in the medium 1 is given by H1 is equal to HI plus HR. Right? So for the medium 1 we will write E1 is equal to EI plus ER and from H1 is equal to HI plus HR. And from the medium 2 E2 equal to ET and H2 equal to HT only. Why? Because the medium 1 we have got two waves, incident wave and reflected wave, and in the medium 2 we have only transmitted wave, that is ET. Field strengths are given by E2 equal to ET and H2 equal to HT. Right? So I think understood everybody how we have written these two. Right? According to the medium 1 properties, we have got E1, H1, E2, H2. Next is according to the boundary conditions. Why? Because there is a boundary which is existed at Z is equal to 0. Below Z equal to 0, we have medium 1 and above Z equal to 0, we have medium 2. So, according to the boundary conditions, why? Because the two medium or we have considered is two dielectric medium. So, according to the boundary conditions, the tangential components of E and H must be continuous at the interface, that is at Z is equal to 0. Right? Tangential components are represented with ET and HT. Similarly, normal components are represented with EN or HN. Okay? So, the waves are transverse in nature means transmitted along with the reflected. So, the waves are transverse in nature at the boundary. The fields E and H both tangential to the interface means both are continuous at the interface. And according to that, according to the boundary conditions between two dielectric media, we have got equations as E1 tan is equal to E2 tan and H1 tan is equal to H2 tan. Simply we can write it as E1t equal to E2t and H1t equal to H2t. Right? So, based upon the field components which are present in the medium 1 and medium 2, the tangential components of both the medium 1 and 2 are continuous at the boundary, and electric field intensities as well as magnetic field intensities of the tangential components of both the medium 1 and 2 are continuous across the boundary. Hence, E1t equal to E2t and H1t equal to H2t. Right? Next. So, at the interface means where is that interface is existing or the boundary is existing means at Z is equal to 0. So, at Z is equal to 0, we are going to write that EI is equal to means in general that eta is given by it is the ratio of E by H. Then from that eta equal to, or from this equation if you are going to write the equation for E, then eta and H are to be multiplied. Or if you are going to write the equation for H, then E by eta are going to write. Right? So these are the three relations between intrinsic impedance eta, electric field strength into E, and the magnetic field strength as H. Right? Electric field strength and magnetic field strengths are also known as electric field intensity and magnetic field intensities. Right? So depending upon those three relations, we are going to write here EI equal to incident wave field strength EI equal to, and incident wave field strength EI is exist in which medium? In the medium 1. Hence intrinsic impedance 1 is given by eta 1 into HI. Right? So where eta equal to E by H, from this E equal to eta into H. If you are going to write the equation for incident wave, all such are represented with EI, eta 1, HI. Okay. So from that EI equal to eta 1 into HI. Similarly, ER equal to minus eta 1 into HR. Why we have got minus here? Why? Because in the medium one, how many waves are exist? Two waves. What are those? Two, incident wave and reflected wave. When the incident wave is strike the boundary, means when the incident wave is traveling towards the positive direction, the reflected wave is traveling towards the negative direction. So two traveling waves are moving in two opposite directions. If you are considering incident wave is in the positive direction and reflected wave will be in the opposite to that of incident wave. Hence, ER equal to minus eta 1 into HR. Okay. Then similarly, ET, transmitted wave, which is equal to eta 2 into HT. Right. So, ER equal to minus eta 1 into HR and ET equal to eta 2 into HT. Right. So, based upon these three relations, EI, ER and ET, we will write the wave equations as mathematically we can write that ET equal to EI plus ER. Why? Because according to the boundary conditions, E1 is equal to E2. Let it be E1t equal to E2t. So in the medium one, what are the two waves which are exist? EI plus ER, and in the medium 2 we have only that transmitted wave is exist, hence it is ET equal to EI plus ER. Let it be considered this as equation number 1, and in the medium 2 means from the magnetic field intensities HT equal to HI plus HR. Okay, so ET equal to A plus ER and HT equal to HI plus HR. Consider this as equation number 2. So from equation number 1, ET equal to A plus ER, from 2, HT equal to HI plus HR. Okay, now consider this equation number 2. In that you just write H by, what is that relation? H is equal to E by eta. So if you are going to write H1 E by eta 1, E1 by eta 1. If you are going to write the equation for H2, then E2 by eta 2. Right? So depending upon that, here EI by eta 1 means HT equal to HI plus HR. Now from this, ET means it is given by ET by eta 2. Why? Because this transmitted wave is existing in the medium 2, hence intrinsic impedance is replaced by eta 2, and HI means EI by eta 1 minus ER by eta 1. Why the here minuses exist? Why? Because in the medium 1, incident wave and reflected waves are exist. Incident wave is traveling towards the boundary and reflected wave is traveling away from the boundary. Two directions are in opposite. Hence, that opposite is resembles with negative sign. Right? So, EI by eta 1 minus ER by eta 1, which is equal to ET by eta 2. Right? So, if you take LCM between these two, now to simplify that equation, eta 1 is common, then EI minus ER equal to ET by eta 2. Okay? Now, from this means ET by eta 2 equal to EI minus ER by eta 1. Now from this, ET or EI minus ER equal to eta 1 by eta 2 into ET. Right? So this is another equation which is represented with equation number 3. Now, keep in mind this ET equal to A plus ER and HT equal to HI plus HR and EI minus ER equal to eta 1 by eta 2 into ET. Right? So, in order to write the equations for transmission coefficient tau and the reflection coefficient as gamma, we will consider 1, 2, 3 equations. Right? So, from these 3 equations, first add equation 1 and equation 2. So, in the equation 1, we have ET equal to EI plus ER, and this is from 1, and from 2, ET means EI minus ER equal to ET into eta 1 by eta 2. Right? See here, if you observe in this equation number 3, that is EI minus ER equal to eta 1 by eta 2 into ET. Consider this as equation number 3, right? So from 1 and 3 equations, by adding equation number 1 and 3. So what is there in the equation number 1? EI plus ER, and in the LHS part or RHS part, first separately add LHS as well as RHS, then EI plus ER plus EI minus ER equal to, in the RHS part, ET plus this ET into eta 1 by eta 2 into ET is exist, right? So here eta ER and this ER plus ER and minus ER gets cancelled, then 2 into EI. EI plus EI is to be added, then 2 into EI equal to, and if we take here ET as common, then 1 plus eta 1 by eta 2 into ET is left out. Now from this ET equal to, means if you take as LCM here, eta 1 plus eta 2 by 2 eta 2, see, 2 EI equal to 1 plus eta 1 by eta 2 into ET is obtained. So eta 1 plus eta 2 by eta 2 into ET is nothing but 2 EI. Now from this ET equal to, or ET by EI equal to, so 2 eta 2 by eta 1 plus eta 2 is to be obtained, and it is the ratio, means transmitted wave field strength to the incident wave field strength, which is denoted with transmission coefficient as tau, and it is given by tau equal to ET by EI equal to 2 eta 2 by eta 1 plus eta 2, right? So how we can define this transmission coefficient tau? It is the ratio of the transmitted field strength to the incident wave field strength, hence tau equal to ET by EI equal to 2 eta 2 by eta 1 plus eta 2. Okay. See, first consider we have got ET equal to EI plus ER, then ET into eta 1 by eta 2 equal to EI minus ER as equation number 1 and 3. By adding equation number 1 and 3 to get transmission coefficient tau. So firstly, if we are going to add LHS parts of these two, EI plus ER and EI plus EI minus ER, which is equal to ET plus eta 1 by eta 2 into ET. So ER and ER gets cancelled, 2 EI equal to 1 plus eta 1 by eta 2 into ET. Now from that, ET equal to 2 eta 2 by eta 1 plus eta 2 into EI. Now transmission coefficient tau can be written as ratio of transmitted wave field strength ET to the incident wave field strength EI, which is nothing but 2 eta 2 by eta 1 plus eta 2. Okay. Similarly, we are going to have another coefficient called reflection coefficient. So in order to derive that reflection coefficient, firstly, EI plus ER equal to ET. This is from equation number 1. And EI minus ER equal to eta 1 by eta 2 into ET. By eliminating ET from equation number 1 and 2, or in order to eliminate this from 1 and 3, if you are equating RHS or else either LHS parts are same, then automatically other part will be same, right? Okay, then EI plus ER equal to ET and EI minus ER equal to eta 1 by eta 2 into ET. So to equate these two, we are supposed to write the equation for ET from the equation number 3. Then EI minus ER into eta 2 by eta 1 equal to, okay. Then now if you compare these two equations, EI plus ER equal to ET. Now from this, EI minus ER into eta 2 by eta 1 equal to ET. Now by comparing these two equations, we have got EI plus ER equal to EI minus ER into eta 2 by eta 1. See here, if you observe, EI plus ER equal to eta 2 by eta 1 into EI minus ER, right? So in order to simplify this one, first eta 1. So cross multiplication between these two, we multiply this EI plus ER into eta 1 and eta 2 into EI minus ER. then we are going to get here eta 1 into A plus ER equal to eta 2 into EI minus ER. Okay, so from this, now to simplify this equation, eta 1 EI plus eta 1 ER equal to eta 2 EI minus eta 2 ER. Okay, now separate the eta 1 terms and eta 2 terms. Hence, eta 1 EI minus eta 2 EI equal to, take this term into this side and this term into this side, then minus eta 1 into ER minus eta 2 into ER, or eta 1, suppose if we take EI as common, then eta 1 minus eta 2 equal to minus of ER if we take as common, then eta 1 plus eta 2 is left out, right? Now from this, this negative is multiplied with this side, means then it becomes EI into eta 2 minus eta 1 equal to ER into eta 1 plus eta 2. Okay, so now from this, it is the ratio of ER by EI equal to, why? Because here we are going to write the mathematical equation for the reflection coefficient gamma, and it is the ratio of reflected wave field strength R to the incident wave field strength I, right? So ER by EI equal to, now we are going to write eta 2 minus eta 1 by eta 1 plus eta 2, right? So if you observe the reflection coefficient gamma and equal to, it is the ratio of reflected wave field strength ER to the incident wave field strength EI, which is equal to eta 2 minus eta 1 by eta 2 plus eta 1, right? So previously we have got transmission coefficient tau equal to ET by EI equal to 2 eta 2 by eta 1 plus eta 2, right? So here we have the reflection coefficient gamma equal to ER by EI equal to eta 2 minus eta 1 by eta 2 plus eta 1, right? So normal incidence at a plane dielectric boundary case, we have got two coefficients as transmission coefficient tau and the reflection coefficient as gamma. So from these two assumptions, we are going to draw some of the important notes, means 1 plus gamma equal to tau. So how this relation has to come? 1 plus gamma equal to tau means 1 plus, what is the gamma equation? As we know that gamma equal to ER by EI equal to eta 2 minus eta 1 by eta 2 plus eta 1, right? So 1 plus gamma means eta 2 minus eta 1 by eta 2 plus eta 1 equal to so if you find the LCM between these two and simplify the equation, then eta 1 plus eta 2 plus eta 2 minus eta 1 by eta 1 plus eta 2 equal to, so minus eta 1 and plus eta 1 gets cancelled, 2 eta 2 by eta 1 plus eta 2. Now what is this relation? 2 eta 2 by eta 1 plus eta 2 is nothing but is the ratio of transmitted wave field strength to the incident wave field strength as ET by EI, nothing but it is tau. Okay, so from this two equations, reflection coefficient and transmission coefficient, 1 plus gamma equal to tau, we have written. One more relation, that is 0 is less than or equal to modulus of gamma is less than or equal to 1, means reflection coefficient gamma is ranging from 0 to 1, right? So generally the range of the reflection coefficient means it is ranging from 0 to 1, and why we have got we have written this modulus of 1 means basically it is the ratio of gamma equal to, it is the ratio of minus ER to EI. If you find its magnitude, then it becomes ER by EI, right? So one of the equation equal to 0, how we are going to get the value of that? Another one and if it is equal to 1, how it is to be obtained? Depending upon that, the range of this reflection coefficient is ranging from 0 to 1. Okay, now both the coefficients means depending upon that, first the range, now to find this range gamma, see this is the general equation for that. Suppose if we got gamma equal to 0, means eta 2 minus eta 1 by eta 2 plus eta 1 is equal to 0 for the first case. Now from this, eta 2 minus eta 1 equal to 0, then eta 1 is equal to eta 2, right? Means this is the case, there is no, we have got some transmitted wave. Similarly, eta 2 minus eta 1 by eta 2, 1 plus eta 2 is equal to 1. This is the case. Now, eta 2 minus eta 1 is equal to then eta 1 plus eta 2. Now, if you separate these two terms, eta 1 is equal to eta 2, eta 2 equal to eta 2, then minus eta 1 is equal to eta 1. From that, eta 1 equal to 2 eta 1 is equal to 0. Now from that, eta 1 is equal to 0. So depending upon this, the range of this one is given by reflection coefficient gamma is given by 0 to 1. And both the coefficients tau and gamma are dimensionless and may be complex in nature. Why these two are dimensionless? Means it is the ratio of generally tau, it is a coefficient, and it is a ratio of Et by Ei. Generally the unit for E is nothing but volts per meter, and both are getting cancelled, means Et by Ei equal to volts per meter gets cancelled, we'll get one constant. Hence, and similarly this reflection coefficient gamma also. Hence, from both the coefficients, reflection coefficient gamma and the transmission coefficient tau are dimensionless, and both may be complex in nature, right? So now to prove that, means incident wave field strength is a combination of reflected as well as transmitted wave. To prove this statement, we are going to consider one theorem called pointing theorem, right? So pointing theorem gives the relation for power, and it is given by here average power. Now to find that average, we are supposed to consider it as 1 by 2. Now P average is equal to, so Em square by eta. Why Em square by eta? So in general, what is the formula for power? P equal to Vi, or sometimes V square by R, or sometimes I square into R. V and I are related by here electric field strength E and the magnetic field strength as H. Hence, we can write these two are EH is equal to, or E square by, or R is nothing but intrinsic impedance as eta, or H square into eta, right? Depending upon that, medium 1 and medium 2, we are going to consider E square, EI square, or HI square, HR square, HT square, like that, right? So in general, this average power density P average is given by 1 by 2 into Em square by eta. Why? Because EH is equal to, as we know that E and H means intrinsic impedance eta is equal to E by H. Now from that, H is equal to E by eta. Now if we write in place of H by eta, then E square by eta, or H square into eta, like that. So now to write the equation for average, we just consider 1 by 2 into Em square by eta. Here Em is the magnitude of the electric field strength. And generally, this power is measured in watts and power density, hence watts per meter square, power per unit area. And the units are written as watts per meter square. Next, the average incident power in the medium one. So to write the equation for incident wave power, so Pi average, I stands for incident wave and P average is average power density, which is equal to, in general we have written P average is equal to 1 by 2 Em square by eta. Depending upon the medium 1, medium 2, we are going to write incident wave, reflected wave and transmitted wave fields, strengths, right? So Pi average is equal to 1 by 2 into Ei square by eta 1. Why? Because incident wave, So Ei square by eta 1. Why? Because incident wave is existed in medium 1, hence intrinsic impedance is given by eta 1. And for the average power reflected in the medium 1 is 1 by 2 into Er square by eta 1, and R stands for reflected wave. Similarly, the average power transmitted in the medium 2. So the transmitted wave is in the medium 2 only. Hence, PT stands for transmitted wave. So, PT average is equal to 1 by 2 into ET square by eta 2. And in general, we know that the average power density or power density is measured in watts per meter square. So, incident wave power density is given by half into A square by eta 1. For reflected wave, it is half into ER square by eta 1. For transmitted wave, it is ET square by eta 2 into 1 by 2. Right? Depending upon these three relations, we are going to consider as the ratio of power transmitted to the power incident. So hence it is power transmitted, that is PT average to the incident, PI average, equal to 1 by 2 into ET square by eta 2 into 1 by 2 into EI square by eta 1. Right? So in order to simplify this one, these two gets cancelled. ET square by EI square into eta 1 by eta 2. Or in general, we are going to write ET by EI whole square into eta 1 by eta 2. So what is the CT by EI transmission coefficient? Nothing but 2 eta 2 by eta 1 plus eta 2 into eta 1 by eta 2. This as whole square. Right? So from this we are going to get eta 2 and this eta 2 gets cancelled. Then 2 square becomes 4 eta 1 eta 2 by eta 1 plus eta 2 whole square. That is PT average by PI average equal to transmitted wave power density to the incident wave power density is nothing but 4 into eta 1 eta 2 by eta 1 plus eta 2 whole square. Right? As we know that transmission coefficient tau, it is the ratio of transmitted wave field strength to the incident wave field strength, and it is given by 2 eta 2 by eta 1 plus eta 2. Then the ratio of power reflected to the incident. So firstly we have considered transmitted wave to the incident wave. Now we will consider here reflected to the incident. Hence PR average by PI average equal to half into ER square by eta 1 and half into EI square by eta 1. So this half and this half gets cancelled. Now ER square by EI square into eta 1 by eta 1. Both gets cancelled. Then ER by EI whole square is to be obtained. What is this relation? ER by EI? It is the ratio of reflected to the incident wave is given by eta 2 minus eta 1 by eta 2 plus eta 1 whole square. Okay, so this is gamma, then that is this PR average by PI average equal to eta 2 minus eta 1 whole square by eta 1 plus eta 2 whole square. Right? Since we know that ER by EI equal to eta 2 minus eta 1 by eta 2 plus eta 1. Okay, so previously we have got PT average by PI average. Then next is PR average by PI average. Okay, so by adding these two, PT average to by PI average plus PR average by PI average, which is equal to. So how we are going to get PT average by PI average is 4 eta 1 eta 2 by eta 1 plus eta 2 whole square plus eta 2 minus eta 1 by eta 2 plus eta 1 whole square. Okay, so in order to simplify this one, 4 eta 1 eta 2 plus this in the numerator eta 2 minus eta 1 whole square means we can expect this one a minus b whole square formula, then eta 1 square plus eta 2 square minus 2 eta 1 eta 2 by the LCM denominators are the same, then eta 1 plus eta 2 whole square. Okay, so 4 eta 1 eta 2 and minus 2 eta 1 eta 2 gets cancelled. Eta 1 square plus eta 2 square plus 2 eta 1 eta 2 by eta 1 plus eta 2 whole square. Okay, so a square plus b square plus 2ab, and the formula is given by a plus b whole square, means eta 1 plus eta 2 whole square by eta 1 plus eta 2 whole square. Okay, so both gets cancelled, which is equal to 1. Now from these two relations we have got PT average by PI average plus PR average by PI average is equal to 1. Now from this we have got PT average plus PI average, PR average is equal to PI average. Means average power density is nothing but is the combination of reflected wave to the transmitted wave. Right? So that is given by here PT average plus PR average is equal to PI average. So initially we have assumed that is when the incident wave is interfaces or strikes the boundary, part of the wave is reflected back to the same medium and part of the wave is transmitted to the next medium. Hence, the incident wave is a combination of reflected as well as the transmitted wave. So that we have proved here PI average equal to PT average plus PR average. Right? So this is about the normal incidence at a plane dielectric boundary. So now to derive the boundary, the mathematical equations for transmission coefficient and reflection coefficient of the normal incidence at a plane dielectric boundary, there we have considered two medium as two homogeneous media, means both the medium 1 and medium 2 are dielectric medium. So now to analyze that, firstly we have got the characteristic equations are sigma is to be 0 as assumed. Now depending upon that, two boundary conditions between two dielectric media we have considered, that is E1t equal to E2t. Now from that, transmission coefficient tau and the reflection coefficient gamma are derived. Now from that we have proved incident wave power density is a combination of reflected wave as well as the transmitted wave. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.